In this video, we are going to see about exponential Fourier series. In this exponential form, the function x of t is expressed as weighted sum of complex exponential functions. The exponential Fourier series can be expressed as x of t is equal to summation n equal to minus infinity to infinity Cn e power jn omega naught t. That is the weighted sum of complex exponential function e power jn omega naught t, where Cn is equal to 1 by t integral t naught to t naught plus t x of t e power minus jn omega naught t dt. Actually, Cn is the Fourier coefficients of exponential Fourier series. Omega naught is the angular frequency which is equal to 2 pi f. We know that frequency is inversely proportional to time period. So, it is actually equal to 2 pi by t. Now, we see an example based on the exponential Fourier series. Now we are going to find the exponential Fourier series representation of a half-wave rectified sine wave. We know that half-wave rectifier pass the positive half cycle of the signal and it will remove the negative half cycle of the signal. The maximum amplitude is V and it will pass the signals from 0 to pi and attenuate from pi to 2 pi. Then again pass the signal from 2 pi to 3 pi and it will remove the signal from 3 pi to 4 pi likewise. Now we can find the solution for this. Given in the question that the signal is a sinusoidal signal with the maximum amplitude V. So x of t is equal to V into sine omega naught t. This is from 0 to pi. And from pi to 2 pi it is equal to 0. We are going to consider for one cycle. Here the signal is periodic with the period t naught which is equal to 2 pi. We know that the angular frequency omega naught is equal to 2 pi by t. So which is equal to 2 pi by 2 pi because here t is equal to 2 pi. So the angular frequency is equal to 1. We have to find the exponential Fourier series which is given by x of t is equal to summation n equal to minus infinity to infinity Cn into e power jn omega naught t, where Cn is equal to 1 by t integral t naught to t naught plus t x of t e power minus jn omega naught t into dt. So to determine the exponential Fourier series, first we can find the Fourier coefficients, that is Cn. Here the signal is periodic with the period 2 pi. So to find Cn, we are taking the integration from 0 to 2 pi. In this range of 0 to 2 pi, 0 to pi only we are having the sinusoidal signal which is given by V sine omega naught t. Omega naught is equal to 1 for this problem. So it is equal to V sine t into e power minus j omega naught nt. Omega naught is again equal to 0. The next range is from pi to 2 pi. Pi to 2 pi the signal is absent, that is it is equal to 0. So we are going to take only the first term. We know that sin theta is equal to e power j theta minus e power minus j theta by 2j. We are going to use this in the next step. In the place of sin t, we are going to take e power jt minus e power minus jt by 2j. In this step, we are going to combine e power jt and e power minus jnt which is equal to e power jt into 1 minus n. Similarly, we are going to combine e power minus jt and e power minus jnt. So, which is equal to e power minus jt into 1 plus n. Now we are going to integrate the first term and the second term with respect to t. So integration of e power jt into 1 minus n dt will be equal to e power jt into 1 minus n divided by j into 1 minus n, and the limit is from 0 to pi. And the second term, integration of 0 to pi e power minus jt into 1 plus n dt, which is equal to e power minus jt into 1 plus n divided by minus of j into 1 plus n. Minus and minus becomes plus, and the limit is from 0 to pi. Now we are going to apply the limit. The upper limit pi, when you are applying, it is equal to e power j pi into 1 minus n. When you are applying the lower limit 0, the term becomes e power 0. We know that e power 0 is equal to 1. So when you are applying the lower limit, it is equal to 1. Similarly, we can apply the upper limit and lower limit for the second term. When you are considering the denominator, we are having j into j term, that is j square. We know that j square is equal to minus 1. Now we take the common denominator 1 minus n into 1 plus n. So the first term numerator is multiplied by 1 plus n, and the second term numerator is multiplied by 1 minus n. We know that a plus b into a minus b is equal to a square minus b square. So that can be applied in the denominator, that is 1 minus n into 1 plus n, which is equal to 1 square minus n square, which is equal to 1 minus n square. In this step, we are going to expand the numerator by multiplying the terms inside the bracket with outside the bracket. Here we are having minus n and plus n, that can be cancelled. In the numerator, e power a plus b, we are going to write as e power a into e power b. That is, e power j pi into 1 minus n can be written as e power j pi into e power minus j n pi. Here we are having minus 1 and minus 1, that can be represented as minus 2. And also we are going to expand all the e power a plus b terms as e power a into e power b. Here we are having e power j pi term. We know that e power j theta can be represented as cos theta plus j sin theta. So e power j pi can be written as cos pi plus j sin pi, which is equal to minus 1. Similarly, e power minus j pi can be represented as cos pi minus j sin pi, which is also equal to minus 1. In this step, we are going to apply e power j pi is equal to minus 1. Also, e power minus j pi is equal to minus 1. And we will get the terms minus n e power minus j n pi and plus n e power minus j n pi, both getting cancelled. When you are adding the two common terms, minus e power minus j n pi minus e power minus j n pi, will get minus 2 e power minus j n pi, and the remaining term is minus 2. Here 2 is common in the numerator and denominator, that can be cancelled. In this step, we are going to represent e power minus j n pi as e power minus j n pi by 2 into e power minus j n pi by 2. Similarly, 1 can be represented as e power j n pi by 2 into e power minus j n pi by 2. So both will be cancelled and it will be equal to 1. In this step, we are going to take the common term outside, that is e power minus j n pi by 2 is common, that can be taken outside. In the numerator, we are having e power j n pi by 2 plus e power minus j n pi by 2. That can be represented in terms of cos theta. We know that cos theta is equal to e power j theta plus e power minus j theta by 2. Here e power j n pi by 2 plus e power minus j n pi by 2 is replaced by cos n pi by 2. So Cn is equal to v into e power minus jn pi by 2 divided by pi into 1 minus n square multiplied by cos n pi by 2. This is true for all values of n. We have determined the Fourier coefficient Cn. Now we have to find the exponential Fourier series, which is given by summation n is equal to minus infinity to infinity Cn into e power jn omega naught t. So the exponential Fourier series x of t is equal to summation n equal to minus infinity to infinity. In the place of Cn, it is equal to v into e power minus jn pi by 2 divided by pi into 1 minus n square cos n pi by 2 multiplied by e power minus jn omega naught t. Omega naught is equal to 1, so it is equal to e power minus jn t. Next, students can do one exercise problem based on this exponential Fourier series. That is, find the exponential Fourier series representation of a full wave rectified sine wave. Here the maximum amplitude is V and T naught is equal to pi. The angular frequency omega naught is equal to 2 pi by T. Here T is equal to 2 times T naught. Therefore, omega naught is equal to 2 pi by 2 into pi, which is equal to 1. And the signal is represented by x of t is equal to b into sine of t for the period of 0 to pi. So the students can find the exponential Fourier series of this full wave rectified signal. Thanks for watching this video.